Assalamualaikum. Chapter 4, Multiple Degree of Freedom or MDOF system are the topic of this chapter. Did you know what is multiple degree of freedom system? Multiple degree of freedom or MDOF is defined by a system whose motion is described by more than one generalized coordinate. Most engineering systems are continuous. Which possess infinite DOF. Infinite DOF require solving partial differential equation, which is difficult to do. Therefore, a simplified continuous engineering system are represented by several ways. First, definable DOF. Next is replace the distributed mass and inertia by a finite number of lump mass or body. Example of multiple degree of freedom system are the three-story building. In this model, the inertia of the system is assumed to be concentrated as 3-point masses located at the floor levels, and the elasticity of the column are replaced by spring. Similarly, the radial drilling machine shown can be modeled using 4 lump mass and 4 spring elements, which is elastic beams. The following procedure can be adopted to derive the equation of motion of a multi-degree of freedom system using Newton's second law of motion. First, set up the suitable coordinate. Next, draw the free body diagram. Then, apply Newton's second law of motion. The basic steps of derivation for translation are shown. Sample question of translational motion. First, draw the free body diagram. The FBD of each mass is shown along with the assumed positive direction for its displacement. We assume that x3 is bigger than x2 and x2 is larger than x1 since the direction of motion of the trolley shows to the right. Next, Newton's second law of motion is applied for each mass. Since there are 3 trolleys which equal to 3 mass, the equation of Newton's second law will have 3 represent 3 mass. Then, the equation is expressed in terms of matrix form. Next subtopic are Lagrange equation, also known as energy method. The equation of motion of a vibrating system can often be derived in a simple manner in terms of generalized coordinates by the use of this method. From the equation, Q dot J is equal to dQj over dt. It is also known as generalized velocity. While capital Qj to the power of n is the non-conservative generalized force corresponding to the generalized coordinate Qj. When capital Qj to the power of n is equal to 0, it is known as free vibration system. As for the sample question, the similar case as previous in translational motion is used. Free body diagram for each mass is drawn first in order to solve the problems. Since there are 3 mass and 3 displacement, 3 FBD include the assumed positive direction is created. From the FBD created, the equation of motion of the vibrating system by using potential energy and kinetic energy equation can be classified. The general equation of potential energy are 1 over 2 kx square, while kinetic energy is T equal to 1 over 2 mx dot square, where k is spring constant, x is the length elongation or reduction, and x dot is velocity. The general equation of Lagrange equation is d over dt in bracket dt dx dot minus dt over dx minus du over dx. By differentiating the expression of kinetic energy, which is T, and potential energy U, and substituting the resulting expression, the equation of motion is obtained for every mass. There are 3 equations of motion obtained since the system consists of 3 masses. From the Lagrange equation obtained, it is then derived in matrix form. Next, we move to eigenvalue and eigenvector. Eigenvalue is a method to obtain natural frequency and mode shape, while eigenvector is the solution to find natural modes. The general equation for linear undamped MDOF system is given by mx double dot plus kx equals to 0. Where m is the mass of the system and K is spring stiffness. Next, x equal to capital X exponent to the power of I omega t. Equation 2 is then substituted into equation 1. The equation is then simplified into the simplest equation, which is negative omega squared mx plus kx equals to 0, which also known as eigenvalue equation. From the eigenvalue equation, mode shape known as capital X and natural frequency, which is omega, can be obtained. The equation of eigenvalue is then rearranged, resulting in bracket k minus omega squared m x equal to 0. The equation is then divided by omega squared. Since lambda equal to 1 over omega squared, the equation becomes x bracket k lambda minus m equals 0. Then it is multiplied to k power of negative 1, resulting in eigenvector equation. Once the natural frequency are known, the mode shape or eigenvectors can be calculated using equation shown, where I is the identity matrix. Moving forward to the sample problem. Determine the frequencies and mode shapes for the system shown in the figure. As usual, FBD of individual mass is drawn. The equation of motion is then arranged based on the FBD. To rearrange the equation of motion, the equation is then arranged in matrix form of mx double dot plus kx equals to 0. Natural frequency can be obtained by rearrange the equation above to k minus omega squared m equals to 0. The matrix is solved by using cross multiplication method. Finally, 2 natural frequency is obtained. In order to find the mode shape, the value in equation of motion is then arranged in the equation shown. Using the previous equation, the value of omega is substituted. The equation denotes a system of 3 homogeneous linear equations in 2 unknowns. The first 2 rows of the equation is used. Thus, the first and second mode shape is obtained. Move on to the last subtopic for this chapter. The general equation for linear undamped MDOF system is mx mx double dot plus kx equals to 0. The solution for previous equation can be solved by the assumption shown below. The most general solution of equation 1, that is mx double dot plus kx equals to 0, can be expressed as a linear combination of linear solution given by previous equation, that is equation 2 and equation 3. When A and V is evaluated using the initial condition and t equals to 0, the equation below is obtained. Move on to the sample question. Find the free vibration response of the spring mass shown in figure. The natural frequencies and mode shape of the system are given. The application of the initial condition in equation 6 for displacement and equation 7 for velocity leads to the equation shown. From previous equation, result for A and V is obtained. The free vibration response of the spring mass shown is obtained by inserting the value of A and V from the previous solution.